algorithm, which of the following would be applied supervised learning to? In each case, assume some appropriate data set is available for your algorithm to learn from. Take a collection of 1,000 essays written on the US economy and find a way to automatically group these essays into a small number of groups of essays that are somehow similar or related. It is not a supervised learning, it is unsupervised learning, because we are not saying that how many groups we want and which document should fall into which group. So it is unsupervised learning. If we go to the second one, given 50 articles written by male authors and 50 articles written by female authors, learn to predict the gender of a new manuscript's author when the identity of this author is unknown. This is supervised because here we need to get only two classes. Either it is written by a male or it is written by a female. So we adjust each time weights. If it falls into a female, then we say whether it is correct or not. If it is correct, then the error will become more, then we need to adjust our weights according to the error. So this process which we adjust weights, supervised means it should come into this, the data point, this class. It is not falling into this class, so it is generating error. I need to adjust the weights. That is supervised model, how we generate a algorithm. So here it is clearly telling us that your output should be only two classes, whether it is written by male or written by the female. So the second one will be supervised learning. The first one, we are not having any control on output. We are just saying that what are the similar documents, you group them. You may get 3 classes, 4 classes, or only one class. We don't know that even output, how it looks. But output, we know that if they fall into the same group, then they are similarly related. So the first one is non-supervised, second one is first one is unsupervised, the second one is supervised. Is it clear?
Yes, sir.
Yes, sir.
Is it clear really, or you are just saying that whatever says okay, we will say please, yes, yes.
No, sir, we are here.
It is understood, right?
Yes, sir.
First one is unsupervised, because we don't have any control on output. We can't say which is right, which is wrong, how much of error, those things we cannot determine. So we cannot adjust the weight or even model. The second one, we can adjust the model. We know that we get only 2 classes, so we are supervising whether it is falling into the right class or not. Okay, we will move to the
Yes,
third one.
third one.
So linear regression with one variable where by deriving cost function. See, this cost function, we need to find out theta where h theta x minus y is minimum, right?
Yes, sir.
We need to find those weights such that this h theta x minus y should be minimum. If you substitute any other theta, then that should be more than this h theta x minus y, which theta we found. That is what we need to find, we need to adjust the weight. So in order to minimize theta naught, theta 1, why are we considering of n 1 by 2n? Is it that it minimizes the value of cost function? So somewhere mentioned in the video 2, 1 by 2 have not 1 by 2 is not having much meaning here, because in your expression you take h theta x minus y whole square, but when we are calculating by using the gradient descent or even normal equations, we need to differentiate h theta x minus y whole square with respect to theta. Then we will get 2 times of h theta x minus y. You will get that 2 will cancel. For that purpose, he is taking 1 by 2. So the underline is whether you make h theta x minus y whole square minimum or of h theta x minus of m of whatever m is the average, m points are there. So whether you make 1 by m will come anyway. 1 by m sigma h theta x minus y whole square. If you say that theta is such that it makes h theta x minus y by m minimum, sigma h theta x y over h theta x minus y runs through m minimum. Same theta also makes minimum 1 by 2 of that. Suppose if I say that, let's say, you have values from 1 to 10, x value, and you are taking x square. So where is the x square maximum or minimum? Suppose if you take x square minimum, at 1 x square is minimum because your x square values will become 1, 4, 9 like that. So for x equal to 1 you are getting 1. In x squares your minimum you are achieving at x equal to 1. If I say that at the same x you will also have half x square minimum. If you take half x square, then the first value is 1 by 2, second value is 4 by 2, third value is 9 by 2. You consider like that. Then where will you get half x square minimum? Same, x equal to 1, at x equal to 1 only you get half x square is also minimum. So for that purpose, let's see, we are interested to find out theta. We are not interested to find out here cost function, what is minimum cost, all those things. We are finding theta where cost function is minimum. At the same theta, you will get the half cost theta, half cost function also minimum. If cost function is minimum at theta, if you take half cost function, that also minimum at the same theta. So to find the theta, whether cost function is minimum or half of the cost function is minimum, you will get the same theta. We are interested to find out theta, right? So 1 by 2 is using. Later when we differentiate, the 2 will cancel, your formula looks somewhat nice without having these constants 1 by 2, something like this. Or 2 if you don't use 1 by 2, then you will get 2 times of that in the final formula. So in the calculation he is taking initially 1 by 2 so that he knows when he gets 2, this 2 will cancel if the formula looks nice, but still finding theta, whether half h theta x minus y whole square or half h theta x minus y minimum, will get the same theta. I don't know whether I answered it correctly or not. So if you don't understand, tell me, right? Ask is only to simplify the final formula.
Yes, sir.
If you don't put half, then your formula always comes like 2 times of something. So he doesn't want that in the final formula.
Okay.
And whether you make half of cost function minimum or cost function minimum, the same theta you get. If cost function is minimum at theta, half of cost function also should be minimum at theta only. You don't get other theta where half cost function will be minimum, but cost function is not minimum at that theta. Okay?
Yes, sir.
So we will move to the next one.
Yes, sir.
Let f be some function so that f theta and theta 1 outputs a number. For this problem, f is some arbitrary unknown smooth function, not necessarily the cost function of linear regression, so f may have local optimum. Suppose we use gradient descent to try to minimize f theta naught theta 1 as a function theta naught and theta 1, which of the following statements are true? If the learning rate is small, gradient descent ends up taking an extremely small step on each iteration, so this would actually slow down the convergence of the algorithm. If the learning rate is small, gradient descent ends up taking an extremely small step on each iteration and therefore can take a long time to converge. Both are saying same, right? So this would actually slow down the convergence. It's saying that can take a long time to converge. What is the difference between these two sentences? Do you find any difference between these two sentences?
No.
When it is becoming slow means it takes long time to converge, right?
Okay. Therefore, can take a long time.
What slowdown means what? The convergence will take more steps. Means what? You need to do more iterations. Means it takes more time to converge. Do you find any other meaning in two sentences? They are mentioning two different things.
Up to iteration same, right? Only differentiating, therefore can take long time to converge. So this would actually slow down the convergence of the algorithm.
One is mentioning in terms of iterations, other one is mentioning in terms of time. It takes more iterations, it takes more time, right?
Proportionally both are same.
And learning rate is small means you are removing that slope, little slopes to reach that zero slope.
Okay.
At maximum or minimum, you will get the slope is zero. You need to get that zero, right?
Yes.
Take the slope, the first tangent. Let's say if you see the videos, the first tangent is the slope of the curve at that point. You want a point where the curve will have zero slope. So you are taking that slope and removing something from that, removing something is alpha of slope, so that you reach to this zero.
Okay.
So if alpha is small, then you are removing less slope, so it takes more time. Instead of, you started with 90, you are removing 2 to, then 90 minus 2, it will come something like 96, 88, 86, like that. If you take 1, then first time it will give you 89, second time it will give you 88. So if alpha depends, if alpha is small, then you need to do more times the same process.
Okay.
So the both statements are true. Okay?
Okay.
If alpha is a high value, if you take, it converges fast, but there is chance that it may cross over 0. You may not reach to 0. After you get 1, if your alpha is more, suppose 3, 1 minus 3, you go to minus slope, minus 2 slope. You won't get the 0. So there is problem to take small alpha, to take high alpha. So always alpha should be moderate. We should monitor that. It shouldn't be very slow or it shouldn't be very fast. If it is fast, then it may cross over the 0. It may not reach to 0. Just when it comes to the 0, then it may jump other side than getting into the 0. If you take the small alpha, then you need to do more iterations to reach that 0.
Yes.
Does it answer your query?
Yes, sir.
In normal equation method, to solve for theta analytically, how are we arriving at theta? X transpose, X inverse, X transpose. Right. See, it is, you can see any Google resource for that. He hasn't proved these equations. He has given you the final equation. So he just said that delta, that say you have an equation, that equation should be, this equations will get delta by delta theta j theta equal to 0. If you solve all these equations, he is not deriving that. See, if you want to derivation of that, go by any statistics book, linear regression, normal equations in the Google, or take any statistics book and see. There they explain normal equations for multilinear regression. So these are the equations which you get here, delta by delta theta j theta equal to 0. Those equations you need to solve analytically. This is not your gradient descent method. So mathematically you need to solve all these equations. That if you put those equations, means by doing this differentiation, taking this j theta, then delta by delta theta j, then h theta, you substitute what is h theta. Actually, h theta is your expected value, your predicted value. That predicted value is a theta. This is j theta he has written. Before that, he has to write what is h theta. H theta he has taken something like theta naught x naught plus theta 1 x1 plus theta 2 x2. So then differentiate with the delta, then you get several equations. If there are 5 inputs x, x1, x2, x3, x4, you will get 6, x0 will add. So 6 different equations will get delta by delta theta j theta, j runs from 0 to 5. That is 6 equations you get. So those 6 equations will be simultaneous equations in terms of x and theta. So in engineering you studied how to solve simultaneous equations by using matrices. So if you use that theory, then that will turn out finally theta equal to this equation. So this derivation is not given. If you are more interested to get the derivation, just see normal equations. So here you need to know two things. How to get the normal equations? Normal equations are nothing but delta by delta theta j theta, j is equal to 0 to the number of inputs you have. So that will give number of inputs plus one equation. Those equations, once you get those equations, you should know how to solve those equations by using matrices. So those matrix methods will be discussed in any mathematical book or even the statistics book where they derive. Then you get theta, final answer will be like this. So if you are more interested, then you can go and see those things, right?
Okay.
Does it solve your query at least right now?
Yes, sir.
Yes.
You see, what I am saying is, if you are more interested, just see derivative of normal equations for multilinear regression. Then they will show you each step by step. He has not shown here step by step. But anyway, see, we are not going to use that for our algorithmic purpose. We always use only gradient descent, which is easy to implement in algorithm or computer. This you have to do mathematically. Then you need to learn mathematical methods to use these normal equations. So that's why in your exercises also you use only gradient descent method. So the next is in classification method for finding the hypothesis. How are we arriving x theta x equal to theta transpose x? I did not understand this problem completely, but what I understood, in classification or in regression also, you see, you are taking, in classification, he converts this function into what? This theta transpose x is for linear regression. In classification, this will become 1 by 1 plus e power minus z, that z equal to theta transpose x. Where you got this, I don't know where you got x theta x equal to theta transpose x in classification. Who wrote this query? I am asking them that where you got this equation x theta x equal to theta transpose x for classification. This is true for linear regression.
Yes, sir.
For classification, this will become 1 by 1 plus e power minus theta transpose x.
You got this query?
He says you see logistic regulation, sigmoid function. First he defines, we want a function which will land between 0 and 1. As it extends to minus infinity, it should land at 0. As it extends to infinity, it should land at 1. So that's why that sigmoid function we got. So to get the sigmoid function, we need 1 by 1 plus e power minus z, where z is nothing but your theta transpose x. So h theta x will become 1 by 1 plus e power minus theta transpose x. Okay, anyway, see, you go back and see.
Yes, sir.
If it is still there, you find that reference, right? In each PPT or slide, he is discussing about h theta x equal to theta transpose x. Okay?
Yes, find some reference. Okay, sir.
Yeah. So in the above hypothesis equation, can we assume the value of theta? So if you solve this equation, you are not assuming here. It is just saying that if you solve this by regression method, you will get theta naught equal to minus 1, theta 1 equal to 0, theta 2 equal to 0, theta 3 equal to 1. You see, it is normal geometry that you need this boundary, that pink color one. So what is the equation? Color 1, x square plus y square equal to some constant. So even if you solve by using linear regression, he is explaining here that you get theta naught equal to minus 1, theta 1 equal to 0, theta 2 equal to 0, theta 3 equal to 1, theta 4 equal to 1. So we are not assuming. In fact, see, in linear regression, we will assume, means we will initialize the values, all with zeros or our small values. Then they converge to these values. So we can assume means in the process of algorithm to find the theta naught, theta 1, theta 2, you should initialize, so you can assume whatever values you want. But they should be near to 0, 0, minus 1, 1, 1, then they will converge faster. Otherwise, they take more time. So you cannot assume as you want. After assuming, you need to use the algorithm to refine those thetas. Finally, you get those thetas as minus 1, 0, 0, 1, 1. That is what he meant here. Okay?
Yes, sir.
getting answer okay?
Yes, sir.
Yes, sir.
What is the difference between gradient descent and normalization? At what point of time we need to use them? Normalization will give you accurate thing, right? At one iteration you get, you are solving those equations mathematically. Then you get a direct answer. But the problem is, can you solve mathematically those equations? So even to write a program to solve a mathematical equation is difficult. If it is x squared, then you know that the differentiation will become 2x, so immediately you will program by using 2x. So if a new differential equation comes, then you need to do mathematical solution for that. That through programming, what type of terms will come, when the term comes, what is differentiation, all these things are difficult. But if you can know the normal equations, your program doesn't need iterations. So you know each equation, what is solution, what is the minimum, what is the theta, where you get the cost function minimum, at unshot you will get the answer. The problem is, getting normal equations is problem. Means problem is mathematical knowledge you need, and by hand you can solve it. If different functions comes from computer, solving them may be difficult, but MATLAB or Mathematica may have. But even then it is difficult. But gradient descent is what you have a simple, only one calculation, delta by delta z, whatever function comes, one delta theta. So you are taking values directly, putting into that, and iterating one by one, step by step. So this gradient descent will come with the errors. You are not getting accurate solution, but it is easy to implement. So it depends on, even odd equations also can be differentiated with respect to one term, and that is differentiation you can do. You put it into the algorithm, then you will get the answer. So normalization is difficult to implement. Gradient descent is easy to implement through computer programming. But normalization will give you accurate answer, but gradient descent will give you approximate answer. Even if you add 1 point extra or 1 point less, then gradient descent is the same method. You don't need to change the gradient descent. But these normal equations will change. Even if you add 1 more point extra, then your equation will change. The analytical solution of mathematics will change. So it is much more flexible gradient descent. The drawback is it will give only approximate answer. Is it okay?
Okay.
So next, at one point of time, choosing a quadratic equation may not fit to our algorithm, and where will move towards cubic equation. How to identify this problem with a given data? So this problem will be discussed this week. We have a test data set, validation data set, and training data set. So this validation data set will be used to see which type of curve is reducing the error. That we will take finally. So we don't fix our mind that we need to go only linear regression or cubic regression or quadratic regression. So we will design a model on a training data set, and we will find error and the validation set for first model, then second model, then third model. For which model we will get less error, that we will take. So there is nothing like odd and fast rule that you need to take only this. So this again we will discuss this week, second week. Okay, this problem. So are you okay with these answers for your queries?
Yes.
Okay, then can we move to the second week orientation?
Yes, sir.
Okay, thank you. So then we will start the second week orientation.
Thanks.
See, the first week we talked about linear regression most of the times. We can also make cubic regression or quadratic regression which will involve x square x cube terms. But if you have several variables like x1, x2, x3, then the quadratic equation will become x1 needs two terms, right? x1, x2, x3, then x1 multiplied x2, x1 multiplied x3, then each individual x1 square, x2 square, x3 square.
Sir,
Yes.
we are not getting any content on the PDF document.
Okay. This is PDF. I open this PPT then.
Yes, sir.
Is it visible now?
Yes, sir. It's okay. Visible.
Okay.
Yes, sir.
So, first week we tried to get a line. But sir, here he is giving one example that with line you may not classification problem. This is so with lines we may not classify, or sometimes even with the sigmoid function we may not classify. So here you see the plus marks and this zero marks, they are all around the plane. So that's why you need non-linear boundary. Linear means with a line. With a line, if you can separate, it is called linear boundary. But with a line, you cannot separate plus and zeros here, plus symbols and zero symbols. You need something differently, a different boundary, and we don't know exactly how do we get an equation for this pink line. This is boundary which separates two classes. This may involve terms of x, xs, x squares, or multiplication of two terms, x1, x2, or multiplication of three terms, x1, x2, x3, or x1 square, x2. We don't know what type of terms. So he is just mentioning that g may be a function of, we are assuming it may be a function of theta naught x1, x2, x1, x2, x1 square, x2, x1 cube, x2. We can extend to any level, any polynomial. So how to solve these type of problems? The first week we haven't learned that. So this second week we started with this non-linear classification problems. With lines you cannot classify. So how do we get these type of equations? This line equation, this pink line equation may be something like theta 1 x1, theta 2 x2, theta 3 x1 x2. So he starts with this. To do this problem, he is introducing neural networks. So all these slides you can just go through. He is explaining physically how a car can be identified, how sensors will take all those things. I don't want to discuss that. You can go through these videos which are given in your content.
Yes, sir.
This how biologically mind works, what the neurons, how do they work, all those things. So the simple thing in neuron to understand, if I look at a person, immediately I may sense something. Okay, but sometimes we don't remember that who is this person. Then we need to see 2 times, 3 times, then something it corroborate what is there in our mind. Oh, okay, this person is some Ramesh. I met somewhere. It takes some time. So meanwhile, it first look at its face, then it tries to search with in the memory. See any such face seen in the back in some time back, and what is it? So by looking at immediately, by getting some of the features, we don't know actually what features we gathered exactly. That is the beauty of the mind. But it gathered some features. It may see the nose or eyes or ear, something it remembers, which are special to that person. But taking one feature or 2 features, initial values, it may not immediately tell you who is this person. But after some time gathering more and more information, it tell you that who is this person. So these neurons will work, they are called firing. The neurons will fire if it gets sufficient information. If it doesn't get the sufficient information, it doesn't fire. Firing means identifying that person. So when does it fire? Once it fires, right? Even if you get thousands of information later, it doesn't require, even if you get that. So whether it gets enough information or not, that is important for the neuron to fire. So you have only two things, whether to fire or not to fire. So till you get the sufficient information, it is in the not firing stage. Once you get the sufficient information, even if you get more information than bother, it fires. So like that, what is explained how the neuron models. See, these x0, x1, x2, x3 are your inputs. x0 is bias, like your constant term in linear regression. That see, we don't know. Initial itself, the line is some height. So that determines the CNR. So this x0 is bias. So all these things, when will they fight? So mathematically they are understanding that you cannot exactly read what happens in the mind, but they are trying to understand through mathematically a function which says 0 or 1. See, when it gets to the infinity, it is 1. When it gets to the minus infinity, you are getting 0. Last time we have seen this logistic function. So the same function is taking. As x information improves, it fights. Otherwise, it will be at 0 only. Even it fights, slowly it fights, right? As information more and more, it fights to the full. So he is taking a function x theta x equal to 1 plus e power minus theta x. He is saying that, right, these x's, all features may not contribute to the same. That's why we need to get different weights, even in linear regression, logistic regression, all features. Those features are seen at now weights. Earlier we said theta naught, theta 1, theta 2 be solved. What are they? They are just weights. So here also, whenever you have features, each feature may be multiplied with different values. Those values we are putting here theta naught, theta 1, theta 2, theta 3. So if you have 4, x0, x1, x2, x3, 3 are inputs, one is bias unit. So all these units multiplied by theta naught, theta 1, theta 2, theta 3. So the final equation will become x, theta, he is giving theta transpose means it will become a row vector, then theta naught, x naught, theta 1, x1, theta 2, x2 plus theta 3, x3. That is the total signal you are getting from the features. So those, the total is calculated, the total is taken e power minus theta transpose x. So 1 by 1 plus e power minus theta transpose x is between 0 and 1. It may fire, it may not fire in terms of the brain function. So this sigmoid function is used to understand the brain function. Okay? So he is defining a new function. Earlier we were having only theta transpose x in linear regression, but we want this new function. That new function is defining as gz equal to 1 by 1 plus e power minus z. He is calling this as a activation function. That is if you have only inputs. So what he says, okay, in the here we are considering only linear units, like theta naught, x naught, plus theta 1, x1. We are not taking squares, right? x1 square, x2 square, or multiplication of x1, x2. But if you, like non-linear class boundaries, which we have seen just now, to them linearity is not sufficient. You may go to higher order terms. When you go to the higher order terms, there is no end till what you go. And whether they really contribute or also, we don't know. You may take thousands of such higher order terms, but each term whether they contribute or not. If you take thousands of terms, then you need to solve thousands of equations. So that's why what he says, okay, we will take initially linear things, and in the second layer we will put some more weights so that the first layer will contribute in a different way to each second layer. See, when you hear the original videos in the content, you will get more understanding. This is just orientation. I am trying to get the idea. So don't get afraid of these things. You see, it will be clear when you hear more detailed video in your course content. So here the idea is, we want to bring those non-linear units. Non-linear units means higher order terms. So higher order terms, we are putting a second layer. The second layer will consist higher order terms. So those higher order terms will be determined from the first layer. So this is called hidden layer because this second layer here, A02, A12, A22, A32, these are hidden units. Hidden units may be of any form. We are not interested to see only x1 multiplied by x2 unit or x1 square unit. We don't want even to see what type of units they are. They may be some combination of x1, x2, x3, x0 units. That is only we are considering. And we are not interested to find what type of unit is there. So let them adjust. If that is square, then let it be square. If it is multiplication of 2 units, let it be. If it is multiplication of 3 units, let it be. So this second unit, second layer we are using to get the non-linear activation functions. These are called. So what it does, these are fictitious. The first layer is the original input. The second layer, we are taking the first layer input, we are redefining our features here in some sense. So we use all x0, x1, x3, we say A12, similarly A22, A3. So if you see A12, from where it is getting signal, it is getting signal from x0, it is getting signal from x1, it is getting signal from x2, it is getting signal from x3. Okay. So similarly, A2 also will be defined by all these 4 units. A3 also will be defined by all these 4 units. So what is this A12? We don't know that A12 is some signal combination of these 4. Similarly, A22, A32, A03 is biased as X0. So by this unit, you can add one more hidden layer also. If you are not satisfied with those units, those weights or those new features, you can add one more layer. Layer 3, in the simple case, what he is doing, layer 3 is the output. Means your prediction, h theta x is nothing but your hypothesis. Your output is same. So how to get this A12? He is explaining A1, Aij is the activation unit of I in layer J. So AI2 is considering that activation function G of theta 101 x0 plus theta 11 x1 plus theta 121 x2 plus theta 13 x3. What are these theta 10, theta 1? These are the weights. So now A12 is combination of x1, x2, x3. So x1 with theta 101. This 1 is nothing but weights assigned for first layer inputs. If it 2 comes after second layer, here this is second layer weight. So this top one, say in brackets 1 for each theta, that denotes they are the weights assigned in the first layer. How many weights you need first layer? Because x1, x2, x3 are used to determine A12, you will get 3 units with respect to A1, 3 units with respect to A2, 3 units with respect to A3. So this A12, 3 weights are nothing but A1. You are getting weights for A1. Always the top one is the layer number. The subscripts 10. This 1 is this is weight for A1. The second weights you see 2. All 2 are there. Means that is weight for second unit.
Layer.
The third equation you will see all 3s are there. The first subscript. That means that weights you are getting for third unit. So the second subscript, that weight is coming from 0th x0. Here it is not there. Earlier figure you were having x0. That weight is coming from 0th unit. That weight is coming from first unit x1. That weight is coming from x2. The second denotes the weight is coming from 2. This second subscript 3 here denotes the weight is coming from x3. Similarly, he is explained.
Yes.
So now this h theta x equal to A13. This 3 denotes third layer here. So this third layer depends on the previous layer, second layer. So here again, how many weights will come? 3 weights will come. So those 3 weights are weight from A12, weight from A22, weight from A32. So A13 is equal to some theta 102, A02. Same notation, you see. This 2 is the layer, at which layer we are attaching weights. This top superscript. Subscript 1 means for which activation unit you are getting the weights. Here only one A13 disease he is not written here in red circle he has to write A13 because only one is their output, A1 third layer. So you are getting weights for A1, that's why this one is fixed in this equation. This first weight is coming from A02, the bias unit. Second weight is coming from 1. Third weight is coming from 2. Fourth weight is coming from 3, A12. So this is the notation. So this A12, A22, A32 are simply activation functions which are calculated by previous layer units, X1, X2, X3. Once you get this summation he calls Z value, theta 101 x0 plus theta 11 x1. So this he calls Z12, the second one Z22, Z32. Then this is the last one is Z1 3, that is third layer Z1. So this is also called net function. Net means you are calculating net signal from the previous layer. So G of net, G of net, G of net, this G of net. Okay. So to calculate the second layer activation functions, you can also multiply this as a matrix. You have seen that matrix. So if you want to multiply with matrix, is saying that if network H has Hj units in layer J, Sj plus 1 units, layer J plus 1, then theta j will be of dimension because you need to multiply with theta with x0 matrices. So he says Sj plus 1 by Sj plus 1. So this simply you can see the first three equations are between first layer and the second layer. First layer how many units you have? 3. Second layer how many units you have? 3. So what is that will be Sj plus 1 means 3 by Sj. The before layer has 3 units. So 3 by 4 matrix. You see here 3 rows and it has 4 columns. Is it or not here?
Yes.
And if you take last equation, last 2 layers, before layer has 3 and the next layer has 1. Right? So this is Sj plus 1, 1 by Sj plus 1, Sj is 3 here, 3 plus 1. So 1 by 4 matrix. Say 1 row and 4 columns. Between the equation between second and third layers, okay?
Yes, sir.
I'm not hearing sound.
Yes, sir.
Yes, sir.
Okay. So this is how he is calculating this A12, A22, A32, and the G function we are not getting into nonlinear function. We are just taking them as sigmoid functions. So those sigmoid may consist that type of nonlinear terms. Okay. So then we'll move to the next slide. As like this, you can add any number of layers. So not only the first 2 layers. From second layer, you can again assign weights. You can define another. And the second layer may have any number of activation inputs. Here you have activation units only 3, but you can have any number. We discuss about how many units you can have, those things later. But this is equation. So once you get this, then the important thing in this is only one algorithm we study for neural networks. Neural networks is bringing non-linear terms by introducing hidden layers. So you read the PPTs and you also hear the videos, then it will be easy to understand. But the idea of why they are calling the algorithm feed forward error back propagation algorithm. Only one algorithm he describes. So that means, see, you are calculating the hypothesis function from first layer to, you will calculate the second layer to third layer to fourth layer. So finally, last but one layer to the last layer gives your hypothesis functional units. So feed forward means your input will be feeded from forward direction. First layer to the second layer to the third layer to the fourth to the last layer. Error, to correct the same method we will use to correct the weights. Always weights are directly proportional to the error how much you generate for the cost function. So your equations are what? Theta I equal to theta I minus delta by delta theta I, your cost function, right? Delta by delta theta I of your cost function. Whether it is linear regression or logistic regression, even if it is a neural network, the same thing. How many weights we initialize or we introduce, all those weights are to be calculated from the first derivative of the cost function with that weight. That is the basic principle, first 2 weeks of the content. So only one algorithm in some sense of first 2 units, theta I is equal to theta I minus delta j theta by delta theta I, where j theta is cost function, theta I is weight. So those weights we will adjust like that. So here also, to adjust these weights, first layer weights or second layer weights, whatever the, so error will be known at which layer, last layer will give you your prediction, and then you can compare that with the original values, then you can come to know how much of error it is generating on the training data set. Okay, so to know the error, you need to get it to the last point. So feed forward, calculate all activation units till to the last layer. Last layer will give you your prediction. Take that prediction, compare with the original values, calculate your error. So when you get the error not in the prescribed limits, you need to adjust the weights. So to adjust the weights, this error immediately feels that I got not enough signals from the before layer, that's why I am getting error. So this error will be sent to the before layer to adjust its weights. So this layer will have some weights. Here this layer has this theta 102, theta 112, theta 122, theta 132, those. So immediately at this layer what we do, we calculate delta by delta theta 102 to adjust this theta 102. Theta 102 equal to theta 102 minus delta whatever error you got, delta of that error by delta theta 102, you need to do that. That should be done with all these 4 things. So it says that theta 10, okay, I calculate this, but theta 10 says, hey, I haven't done the whole, don't blame me to get the error, only me, because my calculation is based on the previous layer. So previous layer also has some weights. So it says that, okay, I might have contributed some error, I take the blame, but the total blame is not on me, so I will send the same error what I got to the before layer. So before layer also feels that, okay, my weights are not correct, that's why I am getting error. So before layer also try to adjust. So what is happening, error, that propagation means error will be calculated at the last layer. That last layer will ask to adjust weights before layer. But that layer says that I am not the sole person who causing this error, so I will ask my previous layer to adjust its weights, so that that error is flown back from last layer to the first layer. So in adjustment of weights, first we will adjust last layer, last but one layer weights, then last but one, then before layer to that before layer. So your error is sent back from last layer to the first layer. So that's why this algorithm is called feed forward. So you are sending your signals from first layer to the last layer, then that is the first step. Then second step says, okay, to correct the weights, you should send error from back layer, last layer to the back first layer. So that's why this algorithm is called feed forward error back propagation algorithm. So this is the simple idea. You have introduced some hidden units. To calculate those hidden units, we have this activation function. By using activation function, we calculate those hidden units. So we can introduce as many as layers in between first layer and the last layer. First layer is input layer, last layer is the hypothesis layer. So we can introduce 1, 2, 3 We can also introduce how many activation units we want in each layer. So once you introduce, then these are the methods. Then you calculate your activation units from first layer to the last layer. Then you get the error, propagate that error from last layer to the first layer, so that it adjusts its weights. He has not given complete details of the derivation. I have added one resource for the derivation in general resources. You can see the derivation of the neural network. So it's here he is saying that not one layer, you can introduce one more layer. It's a different layers have different number of activations here. So he has given some examples. You can work out these examples and see whether you get as he explains here. Okay. So not one input, one output. Sorry. Not one output. If you can want several output, multi-class regression problem, this is neural networks problem. If you have several classes, then you can have several output units. The same thing. It's each output unit will be calculated by using the previous layers. So method is same to calculate these output units, whether you have one or two or three. So he introduced some matrix notation later to understand that. So this cost function, we are using this. So j theta, you can go through these slides. So he says how you can calculate a1 equal to x, z2 equal to theta 1, a1, a2 means these are a2. This is matrix notation. So A2 will have A2 0, A2 1, A2 2, A2 3, A3 3, A2 3. Then this is A1 3, A2 3, A2, like that. So he is giving the matrix notation of that. When you go through the general resources derivation of, if you are really interested in the derivation, so you can understand how these formulas are generated. So I'll stop it here because you need to go through this content. Then we can have a much more meaningful discussion, and I can also clear your doubts. So the general idea is to include the nonlinear units. We are just bringing hidden layers here. Those hidden layers, we are thinking that we take care of those nonlinear units. And from one layer to the other layer, from first layer to the last layer, we will feed the input so that all activation units will be calculated. The final activation unit is nothing but output that generates error. That error will be back propagated from last layer to the first layer to adjust the weights.
Yes, sir.
So once you adjust the weights, then your error will become less and less.
Yes, yes.
So your algorithm is 2 steps. Calculate the forward activation units.
Yes, sir.
Then calculate error, propagate that from last layer to the first layer, adjust the units.
Adjust the units.
Then again calculate with the new adjusted weights.
Yes.
What is error? Then again propagate till you satisfy. Okay, this error is okay for me. Okay.
Yes.
So I stop here. This orientation of this.
Sir.
The next 2 PPTs are there. Those PPTs are
Yes, sir.
just describes how many layers you need to take, how many activation units you need to take, and how many which today's query, which cubic regression or quadratic regression should be taken, what is bias, what is variance. So simple PPTs, I have gone through them. You can also go through them and write down your questions. We can discuss much more when we meet next. So my simple submission is now, you got the idea of what is neural networks and what is this algorithm. Listen carefully all the videos, write down your questions if you have anything to discuss in the next session.
Yes, sir.
So that is what I advise. Now it is open if you have any questions.
Any queries? Sir, once after gone through the videos, they will come up with doubts, sir, actually.
Right. So today is Wednesday, right?
Yes, sir. Yes, sir.
So how many days you need? 2 days.
2 days.
So Friday we have a meeting here afternoon.
Saturday, sir.
Saturday morning.
Fine.
Sometime 11 o'clock like that.
Okay, sir. No problem.
Or yeah, you fix the time, right? 11 o'clock, something like that, Saturday, and let me know in advance.
Okay, sir. Sure, sir. On Friday itself, we will be letting you know, sir.
Right.
Yes, sir. Yes.
Friday morning, and may need to go to the ANTU. If I don't go there, then we can have that.
Yes, sir.
But you need to organize it, right?
Yes.
Not like now, with the disturbance, these students will not be at one place. You
Yes.
need to give
Yes, sir.
in advance notice.
Yes, sir.
So I understand your problems. So we'll discuss it later, Virabhadra, once you also discuss with the students.
Sure, sir.
So whether it's possible also the Friday day or Saturday, right?
Yes, sir. Yes, sir. Thank you so much for your valuable orientation, sir. Thank you.
Thanks, sir.
You gave a lot of information on neural networks, sir.
Right.
We are having initial idea, and let us go through the content, then we'll get back to you, sir.
Right.
Thank you.
Thank you.
So much.
Thank you, sir. Thank you, sir.
Bye, sir.